Hi everybody. In this video we're going to talk about the search for physical memory storage, the hypothetical search for an engram. The engram refers to hypothetical permanent change in the brain due to learning that accounts for memory. So let's get started. Remember, have your notes out. If you're taking Cornell notes, don't forget to stop, rewind if you need to, and follow this up with your textbook. Okay, so let's get started. We've spoken about encoding and memory storage. We're going to spend a little bit of time today talking about the history of the search for a physical memory trace and what might account for the memory trace known as an engram. So in 1969, Penfield was present during brain surgery on patients who were conscious at the time, and he used probes to stimulate brain areas while people were conscious during their brain surgery. And on at least one occasion, when stimulating a brain region, a patient reported some long-lost memories, such as I hear my mom calling me when I was a child out in the fields or the woods. And he basically believed that he found the seat of memories, that whole memories are located in certain areas of the brain. And later on, one of the very famous memory researchers, Elizabeth Loftus, refutes this claim and said, not so fast. This wasn't a reliable capability. This was only one or two patients, and it wasn't easily replicated. So she doubted that Penfield had actually found that memories are stored as wholes. Some other history of research: Lashley in 1959 had taught rats to run a maze, a simple maze, turn left, turn right, turn left, to find food until they could reliably run that maze very easily and quickly. He then lesioned parts of the rat's cortex, various parts, and lesion means to destroy. So remember, if you see this term, it means to destroy either with a physical scalpel or a laser in today's surgery. After the rats recovered from the surgery, he put the rat back in the maze, and they were able to run that maze for the most part. There were some times when the rats were unable to, they froze, unable to make a turn, but then when moved in the maze, they were able to complete the maze. So he concluded that memory is not stored in a single space, but in different areas of the brain. Additionally, Girard in 1953 had taught hamsters how to run a simple maze for food, several turns. And then after learning that maze, he cooled the hamster down, lowered its body temperature till it developed hypothermia, and the brain stopped. And the rat was then brought back to life. Sorry, this came up a little late, but the brain activity stopped. The rat was, by all intents and purposes, dead. They brought the rat back to life, used the little paddles to start that heart again, and the rat remembered how to run the maze. So when they put the rat back in the maze, even after the rat was brain dead, the rat ran the maze. So the memory trace was intact. Girard identified that memory wasn't just in the electrical activity of the brain. So we move on. There was a little bit of history about the search for the engram, and we talk about long-term potentiation. The theory here is that the synapses in the brain is where the seat of memory lies. So a synapse is a tiny gap between the sending and receiving neuron. This appears to be a very important area for forming new memories. Neural connections seem to be strengthened with increased activity between two neurons, the sending and receiving neurons. So the more it's used, the stronger that connection becomes. Kendall and Schwartz in 1982 studied this tendency in sea snails called the aplasia. And they use the aplasia because their brain is small, but it has very large neurons that are relatively easy to see using appropriate technology. And they don't have a lot of them. They have about 20,000 neurons in their brain. And they discovered that when learning occurs, and they used a squirt of water and an electric shock to condition the aplasia to withdraw its gills, that the more often that combination happened, they noticed the neurotransmitter serotonin was released at certain synapses during the learning, and they found that the synapses became more efficient. So although this picture is a little bit blurry, before conditioning took place, there might have been 3 receptor sites on the receiving neuron. But after continuous exposure and an increase in serotonin at that synapse, that the receiving neuron actually developed more receptor sites. So it became more efficient at receiving the oncoming signal. So the sending neuron, in that case, then needs less prompting in order to get that signal across. So if we continue and we look at this, this is an actual electron microscope showing the aplasia sea snail sending and receiving, or excuse me, the sending in red, the receiving neuron in white, and that after repeated prompting, the receiving neuron develops more receptor sites. So for long-term potentiation, neural firing with increased activity increases sensitivity for hours or longer. So it's like that receptor site is just waiting for that signal to happen. So after experience, it's more ready. So environmental stimulation promotes formation of new synapses, and this occurs as you learn anything in the brain. As you watch this video, you are developing new synapses, new receiver sites along the pathway with which you learn this. And if you use some of the encoding discussions that we mentioned earlier for ways to encode, if using semantic encoding, self-reference effect, etc., and you quiz yourself, you're developing new neural receptor sites as we speak. So the experiences does alter the functioning of synapses, every experience you have. And what if we prevented LTP from happening? What if we prevented long-term potentiation from happening? We prevented serotonin from being released at certain synapse sites. And an interesting study in 1970 found that once LTP occurs, a concussion, electric current doesn't interfere with old memories, but it does maybe with new memories. So Lynch in 1992 placed rats in a container that had water and high cylinder sides, so it's kind of like a bucket. Somewhere in that water, there was a clear plastic platform just beneath the surface, and that rat would swim around and eventually find that platform. And then when taken out and reintroduced to the same environment, the rat would quickly find that platform, even though there was no identifying stimuli on the side of the environment with which to signal that platform. However, when they generated and created mice genetically that didn't have the capability for LTP, that rat would be placed in and eventually find the platform, but then taken out and put back in. It it never found the platform faster, so it's as if they had never been in that environment. So rats that can't develop long-term potentiation don't learn, so their memory doesn't really improve. Some other important information: stress hormones make extra glucose available to the brain for fuel. So when we look at the amygdala, which is a brain area of densely packed neural fibers located at the end of the hippocampus, and we'll talk about the amygdala later, but the amygdala is the seat of aggression and anxiety and anger. So when the amygdala is active, stress hormones secrete through the body. The brain produces more glucose. And notice the amygdala is located right at the end of the hippocampus. Therefore, it has close proximity to the hippocampus, and it does have an impact on how memories are stored, especially what type of memories? Explicit memories. So we're more efficient with stress hormones. That's it for this video. So you might want to review long-term potentiation, maybe the engram, maybe the seat of how new memories are formed. Don't forget to review, and we will see you tomorrow.